All right, continuing on with some more week 5 exam 1 prep. And we have ourselves a problem that I invented. I don't know, I figured I'd make a one that requiring a rigid body thing, and this is what I did. So this is similar but different to the one that we just did over here. This one was horizontal, while as this one's vertical. Some people say an inverted pendulum. So let me see, what color did I pick? I'll go make my FBD, my IBD, with the part having an arbitrary angle. And in reality, this would be a small angle because we'll make a small angle assumption. So one of the first things I do with my forces right here is I'll have an mg. And so this is going to be a key difference from the previous problem, because this mg stays in there. So this is going to be my reaction at the pin Roy and my reaction at the pin Rocks. We're going to assume the mass of the rod is negligible for this one right here. So when it comes to the forces, let's go light blue. We're going to have a force of a spring and a damper. So I'm going to have 2 times the forces of the spring coming this way, and so that's because this one's being pushed and this one's being pulled, so they're both going into to the left. And then we're also going to have the 2 times the force of the damper, because we are going to assume that we're rotating to the right, so that's resisting the velocity, and that's resisting the velocity. Yeah, so they're both being pulled to the left. And because of the rotation, we're going to make a little rotation thing going on there. We're going to have a m times the length times theta double dot, right? So that's the mass times the tangential acceleration. We also, just for completeness, we'll put the mass times L theta dot squared, right? But this one goes away. This is the normal acceleration that gets placed on there. Things to know. We know over here that force, I'll just write as 2. Force of the spring is going to be 2 times k times the distance. And so this is just a little slight irritation when I didn't write out what this distance was going to be. I guess I could call it b, but let's keep it as I have it here. So it's going to be 2 times the stiffness of this length right here, which is L minus A, and that's times theta. And then the 2 times the damping is going to be 2 times C times L minus A, but theta dot, because it's the velocity. So if we go the sum of the moments about O, and because we don't have a rod here, we're going to go ahead and use an effective moment. It's the same thing. And let's see what else do we have. Let's just write them out. So we're going to have, let's go the spring first. 2 times K times L minus A times theta. That's the force, but we need the moment arm that passes through. And so that's going to be L minus A, so that's squared. Same thing true. I want to put in that that's the sign convention. We'll have 2 times C times L minus A squared again. It's for the same reason, theta dot. And then, irritatingly, we're going to have negative mg, but it's going to be times the moment arm here, which is going to be L times theta. And then over on the right-hand side, so that's everything on the left-hand side. And the right-hand side, we're going to have a negative ml theta double dot. But that's the inertial force that's on here. We need an effective moment, so we need another L in there, so it gets squared. So I'm all the way over here on the right-hand side. Let's jump over to the left-hand side. So we'll rearrange the thing. And I'll write it twice. Plus 2c L minus a squared theta dot, and then plus, all right, so I should probably have put all that inside. It doesn't matter. In there. So I'm going to go 2k L minus a squared, and then, but then minus mgl. Yeah, okay, and then theta equals 0. Kind of getting the thing in the way. Did I do that? No. It looks like I got it. So now so you could call that the equation of motion, or you could call the equation of motion where we divide all the way through. I think it makes it just a little bit easier. So you got a 2c L minus a squared over ml squared theta dot. Did I miss anything? No. Okay. Plus, and then this is a little bit longer, 2k L minus a squared minus mgl over ml squared. That's theta equals 0. All right, so there's the equation of motion. Sometimes we'll be asked for that. Now what we'll do, as we did in a previous and many others, we're going to subst our theta is equal to e to the lambda t. We'll say that's the characteristic equation. Theta dot is equal to lambda e to the lambda t. Theta double dot is equal to lambda squared, lambda squared times e to the lambda t. Put them in, and you end up with lambda squared plus 2c L minus a squared over ml squared times lambda plus that whole thing here, L minus a squared minus mgl over ml squared equals 0. And then, in fact, actually, what I should have done is I also should put e to the lambda t is out there, but we don't care about that, right? So that if that equals 0, then it wouldn't work. So only this right here equals 0. And from that, we can put the lambda 1 and 2 is equal to, all right, so let me use another color. So in my other colors, green, we'll say that lambda 1 and 2 are equal to negative c L minus a squared over, and I think I left out a 2. No, the 2 went away because there was a 2 right here, so we want to divide by 2. All right, so ml squared. And then plus or minus, I didn't leave myself enough room. And there's no real way to grab that. So I'm going to go square root. I'll try to fit it in. It's going to be tight. 2. Ooh, that 2 shouldn't be there. That other 2 would have been the same one as this. So c L minus a squared over ml squared. And then that's squared minus, and then you go 2k L minus a squared minus, right on the margin, mgl. That's unfortunate. and over ml squared. So here's something. Okay, so one aspect that we should mention is that this right here is almost omega d. What you have to do, and we'll just go ahead and hit the I believe button for this, is when you go to write the omega d, you flop sides, right? So this guy over here, so this is going to be looking like 2k L minus A squared minus MGL divided by ML squared. And then now that is going to be minus CL minus A squared over ML squared squared. And sorry about getting into there. But okay, so this is our answer. And the description of why you flop the sign. Well, for one thing, this is the type of thing where if this was, we're assuming this is an underdamped type of thing. I mean, just by the fact that we say a damped natural frequency, that only happens when it's underdamped. Because if it's overdamped or critically damped, it doesn't have a frequency. It's no longer a vibration problem. It just dies away. And then also, if we left it in here as negative, it would make this a imaginary number. So those are good reasons why we would switch this around, right? So that when it's underdamped, so therefore this does have it is a complex number. It has complex roots for the lambdas, but this portion of it is the damped natural frequency, because so therefore it's got to be a non-imaginary number. So this thing we have to swap the sides of, so it's not a negative number, because right now in the state up here it is. Mathematically, how that's done, it's a little bit more words and tedious, but essentially we're going to use Euler's identity to try to swap those things out. I could continue with this. That was that in the explanation was a 12-minute problem, so you should be able to do this like in 12 minutes. Here, where we're going to stick some numbers in, let's say that we had that equation, and if we okay, so originally I messed up and I made this 200, and and what happened is I made the thing unstable, because sure enough, this portion over here, this portion over here was smaller than this portion over here, because I did not make the spring strong enough. That would be considered an unstable thing, right? So if this did go to imaginary, from this corner here, the spring would not really, I would say, it wouldn't support this because this mass would be too large and so forth, and so it would just flop over. That's my interpretation of the stability concern. So I increased this to 1,000 so we could throw some numbers at it. So and by the way, we want to make sure we're looking at this thing, this question as written carefully. So I've placed the numbers in here. I said the mass of this thing is negligible, and the sphere is pulled to the left by 10 millimeters and released. Determine the time it takes for the pendulum to make 2 cycles. Well, this is sort of another trick question, because this is not going to matter. I'm sorry about that. But what am I going to say? So I'm going to use the information that I got in part D, or excuse me, in the last one, the part 1, and I will just fill in the blanks right here. So I'm going to go 2 times, let's take a look at what we got before, 2 times K, so that's going to be my 1,000, not the 200 that I decided to change the thing. And then we're going to take 0.5 minus 0.3, right? and that's squared. So let's look back at this right here. All right, so we got that part. Let's take the MGL minus the mass is 10, 9.81, and the length is 0.5. All right, all of that divided by ml squared. So we're going to have mass 10, and then the length of it is 0.5 squared. All right. Now we're going to go minus CL minus A squared. So it's going to go, oh, I think there's actually a mistake somewhere in here. Yes. I made a numerical mistake. I accidentally kept the 2 in this, whereas it should have gone away because of the quadratic equation's denominator, where it has a 2a, and of course a is equal to 1 when we massage the thing over. So my values are going to be wrong right here. I'm going to go back, sorry. So we're going to have a C times, so C is 2, times L minus A, that ends up being 0.5 times minus 0.3, and that thing is squared, and that's divided by 10. This is the mass and the length squared, and that whole thing squared. All right, so I have a mistake in my original right in here. So I have to work out my numbers, and all right, so my first part, okay, so I had already wrote an in-between problem, in-between part of the thing. So I'll say that this right here is 12.38 minus, and now I can just go ahead and calculate without my 2 in there what I had done. So 0.5 minus 0.3, I could have done that in my head, is 0.2. That needs to be squared and multiplied by 2, divided by 10, and divided by 0.5 or squared, or 0.25. All right, so that's going to be, so it's not a whole lot, right? So it's going to 0.0, okay, no, wait, excuse me, 320, okay. So yeah, not a whole lot. So anyway, so that's going to be 12.38 and square root, and I get that that's 3.514. Compared to 3.518. So I made a mistake on the previous one. It didn't really affect. You can actually kind of see how little that had as an effect onto the side. So now we're going back to the ask. Well, determine the time it takes for the pendulum to make 2 cycles. Well, here's the damped natural frequency. So we could say, well, the period is going to be 2 pi over that, or 2 pi over 3.514. So I got to calculate that again. 2 pi. So you have 1.788 seconds. But it says 2 cycles, right? So cheater, I decided to go 2 times 1.788. And we're left with 3.576 seconds. I think I wrote this wrong before, and it should have been I wrote 3.572, but you know, 3 sig figs is good enough. Only off by a little bit. I think I have one more problem left. One more video. Talk to you later.